All right, so let's go ahead and get started for the day. All right, so I put up my videos a bit like yesterday afternoon, so it took a bit of time for them to get posted, and I'm sorry about that. So obviously I don't expect you to have watched them yet. So let me go over what the content that's expected for you this week is. So let's go ahead and see. There we go. Unlike the other couple of weeks, unlike the other semesters I've done this, I've actually given some optional extra credit. So first I'll go ahead and talk about your actual homework that I've given for the week, which for once is not programming. Okay? Your third lab is this big worksheet on algorithm efficiency and basically calculating the big O runtimes of algorithms as well as converting it for different equations. You can turn this in however you like. You can type it up and print it out, right? You can type your answers like set on a separate page and then submit it that way. We're pretty loose with how you get the answers to us. You can upload it. You can print it out. You can print this page out and just get it to us. I don't really care how you do so. All right. So I put the three rules you really have to remember for doing the for figuring out the runtime, and I'll explain what big O is if you haven't had the chance. What big O notation is if you haven't had the chance to look at the videos. But by show of hands, before you came into this class, how many of you knew what big O notation was for this class? So a handful, right? And how many of you had taken, well, not 1166, what's the class after that? 2160s? Yeah, how many of you took 2166 so far? Yeah. So where did you guys learn big O notation?
My professor talked about it in 1060 a little bit.
So your professor, so Dr. Fiore?
Yeah.
Yeah, but briefly mentioned it. Okay. So the idea here, and I'll explain on the board because it makes it easier that way, is that we cannot really, it's really important to ask how fast does this algorithm or how fast does this data structure operate, right? And we can't just time it like, okay, like run the program and time it, for a variety of reasons. One is that you're going to get different times because of the way the CPU is just going to schedule what operations it's going to decide are important at the moment. Another reason is that my computer might be faster than your computer, or your computer might have some newfangled operations built into the processor that are specialized for doing stuff, so that you can do certain operations quicker. For instance, if you've got a graphics card, you can record stuff using different drivers that take advantage of your graphics card to have a very low CPU impact, right? So you can get other stuff done on your while going. That doesn't really have too much to do with that. But the idea here is that computers can be built differently, and therefore they can run different times. Of course, and older processors are generally slower. So instead what we do is we analyze the algorithm itself, and we do kind of a mathematical analysis of it, of basically the number of steps that it's going to require. And I've gone somewhere over them in the videos, and I'll tackle them. But first I'm going to go over what your homework is, and then I'll explain more about these concepts. So for these, I've given you basically these T of n, which is basically the number of steps this algorithm takes. And I want you to translate it to the corresponding big O time complexities. Now here, right, I show you that the first two rules are what's relevant here, okay, for translating it. And it actually ends up being a very easy process. This might be some of the easiest math you've ever had to do. Okay, because it's mainly just saying, oh, I don't have to care about this term. Oh, I don't have to care about this factor. Okay, and I'm done, right? It's very easy to do this translation. The only thing that I'll give you a heads up about are these guys, because these guys are not obvious. You might want to actually Google these series. How many of you have taken Calc 2, right? How many recognize this series? Right? You should. So you guys know that this is actually a bit of a trick question. So look up this series. Google's actually pretty good at figuring out what this is. So next is then answering questions about what are, the data structure we just learned, right? How long did these things take? And so basically analyzing these data structure, giving me an analysis of what the big O runtime is. Here, the third rule comes into play, which is counting the nested loops usually works to figure out how big your big O what your big O notation is, right? If you have a single loop, it's O of n. Generally speaking, the big O of some algorithm, it's pretty easy to figure out. The big O of some algorithm is O of n, where n is the input size. I'll get into this. I'm kind of doing it in reverse because I did it in order in the videos that I put online. To the dth power, where d is the number of nested loops you have, essentially. So if you've got one single for loop, right, one for loop over here, right, and it goes over n items, right, then this is O of n time. But if I have a second loop in here that goes over, that also runs n times, so we have n runs on the outside, and each run runs n times, so it's n times, so it's n squared, right? So 2 nested loops equals n squared, right? N to the second power. 3 nested loops, right, which we aren't really going to see in this class. A good example of that, though, is when you do matrix multiplication. That generally unless you're a really clever mathematician, you're going to have the brute force way to do it is to do n cubed operations, just because there's so many operations to do, and that will take n cubed time. So these, so that's kind of the analysis. So that analysis will help you on this page. This next page, I give you algorithms, and I ask you to the big O stuff. This one, and a lot of these will require research, a bit of research on your own, like space complexity, to think about it. I don't go over space complexity, so you're going to have to ask yourself that, or ask me. And finally, I give you an algorithm that exists only for the purposes of analyzing it. In algorithm data structure class, there are 2 sorting algorithms that we have specifically for the purposes of just doing analysis. BOGO sort and stooge sort. Stooge sort generally comes up in algorithms, though, because that's much more mathematically weird. BOGO sort is fairly straightforward. I'm asking you to analyze an algorithm whose strategy for sorting is to randomly shuffle everything in the list and then check if it's sorted, right? So figure out what the runtime for that is, okay? Last page is here. And now for everything for lab 2, I also want you to give me the big O analysis of that, okay? And generally and I'll give you a hint there, okay? It's a very easy hint. It's probably going to be an O of n algorithm or an O of n squared algorithm. Okay? It's probably going to be one of those 2. Okay? So now what the heck do I mean by those? Okay? Oh, and last but not least, the important thing, you can ask me, did I get this right? And I'll tell you whether you got it right or not. So you have plenty of, so if you get it wrong, if you're not sure about your answer, you can ask me whether it's right or not. I'll tell you whether you're wrong, or what direction you need to go in to get the right answer, and that way you can go back and you should be able to get this one's fairly easy to get an A on, okay? Also for the people for anybody who needs extra time to do or needs extra points, I did put up a homework. I put up an extra credit assignment. This extra credit assignment does not have a due date on it. So, complete this whenever you want to. But this is my incentive for you to learn regular expressions. Each of these pages is worth 5 points. Essentially, you'll have to teach yourself regular expressions, but it's not really hard. There's a link here, which you can click on to bring you to a website to help you learn that stuff, or at least test that out. But it's basically figuring out stuff like I've got a word file over here, a file of words in the English language. And it's like, I like animals. How many words contain the word cat or dog in them? All right, do more words end in ing or ion? These are questions that you can answer if you learn about regular expressions. How many words contain a Q that are not immediately followed by a U? So those kind of questions. Now this one, because regular expressions are language agnostic, you can use them in any language. You are free to complete this assignment in any programming language of your choice. You can even use grep if you want. to do this. And then I've got a second page of questions over here. For reference, this just to make sure you understand that this isn't difficult, or isn't too difficult. It just requires you to put in some time. This was homework I gave over the summer or this is some of the homework I've given over the summer to 1051 students. Okay? So for the students in Python who were taking Python. So this stuff is actually fairly straightforward once you learn it. And it's very useful. Okay? So what is big O notation? So there are three terms that we use to describe that we're going to learn for this chapter to describe runtime of algorithms, right? And then there was other ones I bring up in the video slides, and one of which is useful for your homework. But the three main ones we're going to use, big O notation we're going to use to describe our runtimes are O of 1, O of n, and O of n squared. What does O mean? It means kind of like order of magnitude, essentially. In mathematical parlance, it means this is the worst case scenario. It's going to be no worse than this. Now, computer scientists, mathematicians sometimes cringe because a lot of times we play fast and loose with the rules as programmers because we care more about just getting our ideas across than rigor. So sometimes we use big O to mean like the average case, but that doesn't necessarily mean. But generally, we're talking about worst case scenario. Now, this O of 1 means constant time. It means that essentially it doesn't matter what the input size is. It doesn't matter what the size of your list is, the size of your array, the size of whatever collection have you. It's going to run the same time, no matter the same exact amount of steps, no matter what. For instance, the size operation, right, which returns how big your list is, right? Because that's a variable and you're just returning a variable. It doesn't matter if you have 1,000 items or 1,000,000 items. You expect to get your answer instantaneously, right? If you're printing out a number, right, you don't care how many digits it has, right? It's going to print it, you don't care how long the print operation will print it out all the same, right? Doesn't matter how big it is, it doesn't become more complex to print it out. Okay? So now these two have an n inside of them. One has n squared, one has n. N means the input size, the size of what we're working on. So this is linear time. Although I go in the video, it doesn't always have to be time. It sometimes could be, we could be describing a relationship between energy or a relationship between space. But generally, we're talking about time. Why time do we care about time when we're analyzing our algorithms? Because from an economic standpoint, from like a standpoint of building programs that people want to use, people don't want to wait more than a second for their program to run, and we get very frustrated if a program takes if a web page takes more than 3 seconds to load, you know? So keeping these in mind, time is kind of valuable when you're trying to sell a product. On a more practical sense of the word, time is the one resource that we analyze that we cannot buy more of. You can always buy more space. You can always buy a bigger battery pack. You cannot buy more time. Okay? So given an input size, this says there's a linear relationship between the input size and the amount of time it's going to take. Right? If we were to graph that, it's going to look something like this, or maybe this, where this is the size. This is the input size, right? Size of the problem and the amount of time it's solves. It could look like that. It could look like this. It could look like this. The point is that it's a straight line, right? The idea here is that it's a linear relationship, meaning that if I add in an additional item, I'm adding an additional item's worth of work to do, right? It doesn't impact the amount of work I have to do with the other items in there, right? Right? If I have to grade, like for here, if I've got a bunch of papers to grade, it just takes me a bit. If I've got one more student joins the class, that means I just have like one more exam to grade come exam day. It doesn't add any additional work I have to do for the other students, right? Now, on the other hand, in a quadratic relationship, suppose that I'm actually a bit of a stickler and I'm not just grading the exams one at a time. suppose I'm going through every exam, comparing them side by side, every exam side by side, right? And I'm checking to see, did you copy the answers? Did you copy the person's answer, right? Now that's a quadratic relationship, because for every additional student I have to grade, that means I have to take that student and go through all the other students, right? So if I have 10 students, right, and I had an 11, then I have to make 10 more checks, right? If I add a 12th student, that means I have to check that 12th student against the other 11, right? That makes sense to everybody? That adds, basically adding an item adds not just more work for the thing I just added, but with regards to everything else as well. Okay? And those typically look exactly like this, where the size of the problem goes up in a parabola, right? Just exactly like you'd expect. And the parabola, you can shape it however, whatever. But what the O of n means is that it means we don't really care about what the shape is. We just care that it's a parabola. We don't care about the slope of the line or what constant gets added to it. We just care that it's a line, right? The idea here is that you can draw some, and I go over in the video I say informal, formal theory about this, where you've got this line that represents your algorithm. And that means you can draw some other, the big O of n means you can draw some other straight line, right? And say, oh, my algorithm's never going to perform worse than this, right? It's always going to be some O of n. So that's a quick rundown of the things in the video. Now in the video I go over certain other examples and like bubble sort, but the idea here is that these are the main three times we're going to be dealing with. Constant time always runs the same. Linear time, where there's a linear relationship. I add one more item, I have one more unit of work. And n squared, I add the nth item, and that means I have n more work to do now. I add the nth plus 1 item, and I have n plus 1 more work to do. Okay? So that's how that works out. Now, over the semester, we're going to learn about log n in Chapter 5, and we're going to also learn about log linear time later on, which sits between n and n squared. And the final things that I have to mention is that the reason this is important is because these kind of tell us whether or not the problem we're trying to solve is actually solvable in a reasonable amount of time, right? One of the things I go over is that cracking a password, that a modern password like using public-private key encryption, that works on something like factoring prime numbers, taking a big number and factoring it out. That's an exponential problem. That takes O to the 2 to the nth power. Notice that the n is over here in the exponent rather than in the base. That means that as n grows, this is going to get really big really, really quickly. Okay? Now in this size, for the idea of cracking passwords, this is the number of bits you have. If it's around 40, that's something reasonable. To the 40th power, that's something that a reasonable computer can crack fairly easily. But if I increase that to 41 bits, it's going to take twice as long because that doubled the amount of time, right? And so if you're dealing with something, trying to crack something with 2048, bits of encryption, then it becomes a ridiculous something that's basically saying, yeah, your secrets are probably safe for, until the sun goes out, So these are describing not necessarily, we're not describing whether or not a problem can be solved, because we're describing problems that can be solved by computers. There's a whole host of problems that can't be solved by computers. But we're talking about whether or not these can be solved in a reasonable amount of time by a computer. Okay? So if you see this, it can't be solved in a reasonable amount of time by a computer, unless the problem size is small. Similarly, when you get something like this, which means we have to check all possible permutations of the problem, that also takes a really long time. All right. So with that, you guys can get to work and you guys can ask me specific questions. And do you have any questions about did any of you happen to get the chance to watch the videos? It's okay if you didn't, because I put them up late. Okay. If you've got questions about it, I'm more than happy to answer them. I'm also more than happy to answer questions about the lab that's coming up due.